Okay, let's do more problems from section 3.7. Let's continue our discussion of optimization. Optimization is again the process of trying to find a maximum or minimum, i.e. optimum value of a particular quantity that is a function of another quantity. And we use calculus methods in order to do this. So let's talk about this problem. This problem tells us that a square-based box-shaped shipping crate is designed to have a volume of 16 cubic feet. The material used to make the base cost twice as much per square foot as the material on the sides, and the material used to make the top cost half as much per square foot as the material on the sides. So what are the dimensions of the crate that minimizes the cost of the materials? Okay, so first thing I want to do in this problem is I'm going to draw a picture and assign variables. I'm told that I have a box-shaped crate. I'm told that the base is a square, so the length and width are the same, so I'll call them both x. I don't know what the height is, so I'm going to call it h. I'm told that the volume is equal to 16 cubic feet. And that's about all I know. I have drawn a picture, assigned variables. So I'm going to move on to step 2, which is I want to write some equations. The first equation that seems relatively obvious in this one is I'm told something about the volume. I should probably write a volume equation. That equation is, how do I find the volume of a box? Well, it's length times width times height, so that would be x times x, or x squared times h. And I'm told that this is equal to 16. This would be my constraint equation. It limits how x and h are related to each other. Now that I have that equation, I need to think about, well, what is the quantity that I want to optimize? I'm told here that I want to minimize the cost of the materials. So I need an equation that represents the cost of the materials. Okay. Well, you might think about it in terms of this cost. If I take, say, the cost per square foot times the number of square feet of material used to make the box, the cost per square foot times the amount of material per square foot, then I will get the total cost. Well, this amount of material essentially is the surface area of the box. So maybe I should start by finding an equation for surface area. Okay, let's do that. Take that part out. The surface area, which I'm going to call S, is equal to, well, it's equal to the area of the top, x squared, plus the area of the bottom, also x squared, plus the area of the sides. I have one side is x times h, and there are 4 sides. I'm splitting it up like that because the area of the top and the material used for the top and the bottom are different. They cost different. So I'm going to write their surface areas as 2 different expressions. These are the sides. Okay, so that's total surface area. I'm told, what else am I told? I'm told how the top and the bottom, the cost for the materials on the top and the bottom relate to the cost of the sides. So I'm told that the material used to make the base costs twice as much as the material on the sides, and the material used to make the top costs half as much as the material on the sides. Okay? I'm not wanting to find what the minimum cost is. All I'm wanting to find is the dimensions that make that cost a minimum. So perhaps let's just say, for instance, that the sides cost maybe $1 per square foot. If that is the case, then the bottom, well, that's twice as much. So it's $2 per square foot. And the top would cost half as much, 50 cents per square foot or a $0.50 per square foot. I'm going to go ahead and input those. Let's say cost C is equal to, well, if the sides cost $1 per square foot, the top costs half as much as that. So half per square foot. And this is, how could I interpret this? This is the cost per square foot. This is the amount of material. So that total together would be the total cost of the top. I can do similar reasoning for the others. Plus the bottom cost double what the sides do. And then this last one should technically be 1 times 4xh, but I don't really need to write the 1 there. I'm going to simplify a little bit. I have like terms now that I have a cost equation. This is equal to 1/2 x squared plus 2x squared is 5/2 x squared plus 4xh. This is the cost of the materials on the box if we make that assumption that the cost of the materials on the sides is $1 per square foot. Okay. So now what? I have two equations. I have a constraint equation. I have a cost equation. I'll write those down again maybe. V is equal, or excuse me, not V. It is V, but I'm going to write it as x squared h is equal to 16. And my cost C is 5/2 x squared plus 4xh. Okay. I need to now write this equation, the cost equation, in terms of only one variable. So I'm going to solve this equation for h. That seems easier. H is equal to 16 over x squared. And I'm going to substitute that in for h in this equation. So that gives me the cost C is equal to 5/2 x squared plus 4x times h, which I know is 16 over x squared. I can simplify that. That gives me 5/2 x squared plus 4 times 16, which is 64, divided by, I have an x on top, x cancels with one of the x's on bottom. So 64 over x, which for calculus purposes, I'm going to rewrite as 5/2 x squared plus 64x to the negative 1. So that's my cost equation. And I could do a little bit more here. I know that this is now a function of only one variable, x, so I could write it as c of x, just to specify that. I have a cost equation. It is an equation of the that is a function of only one variable. I can now bring in calculus to find possible dimensions that will minimize this cost equation. So let's do that now. C of x is equal to 5 halves x squared plus 64 x to the negative 1. Oh, before I do that, let's find the domain of this equation. The domain? Well, let's see. X is again a length, so it cannot be 0. X has to be greater than 0. And you might recall that h is equal to 16 over x squared. That's our constraint. As x gets larger and larger, I will still get a value for h. It may be a very small value, but I will still be able to find a value for h, no matter how large x gets. So x is technically, it could be any real number. So its domain is 0 to infinity. So this is not defined on a closed interval, it's defined on an open interval. So the only locations that I can look for to find minimum values for cost are critical points. That was step 4 in that checklist. Let's go on to step 5 and let's find those critical points. I'm going to find where that first derivative is equal to 0, or that first derivative of the cost equation does not exist, which means I need the derivative. C prime of x is equal to 5 halves times the derivative of x squared, which is 2x, plus 64 times the derivative of x to the negative 1, which is negative x to the negative 2 power, which is equal to 5x minus 64 over x squared. That's C prime. Let's find where this is equal to 0. C prime of x is equal to 0 gives me where 5x minus 64 over x squared is equal to 0. I'm going to multiply both sides by x squared, which tells me if I distribute the x squared, that 5x cubed minus 64 is equal to 0. I will add 64 to both sides. So 5x cubed is equal to 64. Divide both sides by 5. I get that x cubed is equal to 64 over 5. I'm going to take the cubed root of both sides. And I get that very exciting solution of cubed root of 64 over 5, which is cubed root of 64 is 4 over the cubed root of 5. So one critical number for that particular criteria. Okay. Remember again, C prime is equal to 5x minus 64 over x cubed. If I want to look at the other way to find critical numbers where the derivative does not exist, I can note that this occurs at x equals 0 because that will cause division by 0 in this part of the equation, but 0 is not in the domain. The domain must, it only includes positive x values, so I can disregard that critical number. I only have one to check. So my critical number, I'll write it down again, is x is equal to 4 over the cubed root of 5. Now, that is a possible location of a maximum or a minimum cost. I need to make sure it gives me a minimum cost. I cannot assume that that is what will minimize my cost. So let's use calculus to check. This is step 6. I'm going to use the first derivative test. 4 over the cubed root of 5 is approximately equal to 2.3. So I'm going to set up a little number line here. Say this is 4 over cubed root of 5. And I'm going to test values in C prime to the left and to the right of that. Let's test maybe 1 on the left and maybe 8 on the right. C prime of 1 is equal to 5 times 1 minus 60 over 1 squared, which gives me negative 59. All that I really care about is the sign. C prime is negative in that interval. And similarly, if I test 8, C prime of 8, that's equal to 5 times 8 minus 64 over 8 squared, which gives me 40 minus 64 over 64 is 1, which is 39. So that is a positive number. All that I really care about is the sign. What does that tell me? That tells me that the function, cost function, is decreasing to the left of 4 over cubed root of 5, and it is increasing to the right of 4 over cubed root of 5, which tells me that this critical point is in fact the location of a minimum cost. So that gives me the x value that will minimize cost. So if x is equal to 4 over the cubed root of 5 and h is equal to, what is h? 16 over 4 over cubed root of 5 squared. If I simplify that, I get cubed root of 5 squared. So my h value is this. So if x is that and h is that, then the cost is minimized. Cost is minimized. And that finishes up that problem. I think I'll give you one more example in another video.